Two stars orbiting each other are called binary star systems. These systems were first discovered by William Herschel, and you can learn more about his discoveries here. Orbiting stars are shown to exhibit specific properties that can relate to each other, and we can write them down in a simple formula. And I say simple because there's only 3 parts to it. The first part is P, which stands for the period of orbit, or how long the stars take to revolve around each other. The second part is A, which is used to describe the distance between the 2 stars. And finally, the third part is M, which we're solving for, that stands for the combined mass of the 2 stars. The example problem I was given states 2 stars orbit with a period of 830 days. They are separated by 7.2 times 10 to the 8 kilometers. Find the combined mass. Before we can start plugging numbers into the equation, we need to understand how it works. So here's what it looks like. Now this may seem intimidating at first, but after a couple steps I promise it will be much clearer. First, in order for this equation to work, we need to convert the units. We were given a period of 830 days, but we need to convert it to years. Simply enough, just divide 830 by 365, or the amount of days in a year, and you'll have a new number that will work in the equation. You should have gotten something like 2.274 years. They told us the 2 stars were separated by 7.2 times 10 to the 8 kilometers, which is the same thing as 72 with 7 zeros behind it. But we need to convert the kilometers into a much larger measurement of distance known as the astronomical unit. This measurement is just the distance from Earth to the Sun, so if we take that big number of kilometers and call it 1 astronomical unit, or AU, then we can measure much greater distances more easily. So here's how to do that. Take the 720 million kilometers we were given and divide it by 1 AU. 1 AU is equal to 149.6 million kilometers, or 1.496 times 10 to the 8. So divide 7.2 times 10 to the 8 by 1.496 times 10 to the 8, and you'll have a new number which will fit better in the equation. The number should be something around 4.813 AU. Now that the given information has been converted into the proper units, let's place them into the equation and figure out how to work them with each other. Taking p squared years equals a cubed AU over the mass of total solar masses, and incorporating the variables, we get 2.274 squared equals 4.813 cubed over m. But seeing as we need to solve for m, the equation must be rearranged. Since a is being divided by m, just simply multiply m on both sides. That will look like. To finish rearranging, we need to get m by itself, so divide both sides of the equation by 2.274 squared, and here's what that will look like. The next step is to multiply by the exponents, so we'll have m equals 111.493 over 5.171. Now we can calculate for m, which comes out to 21.561. Even though now we have a number for m, we are not quite finished because this number as it stands is actually in solar units. This means the number we have now is a little bigger than if our sun was 21.5 times more massive. When we converted the units in the beginning, we were setting up the equation to where the first answer comes out in solar units. These solar units are not the same as astronomical units, however, because solar units measure mass, not distance. 1 solar unit is equal to 1.99 times 10 to the 30 kilograms, otherwise known as the mass of our sun, and we can use this measurement to better relate the mass of these very large stars. A kilogram is easier for someone to comprehend though, so that's why it's used as a standard unit and why we should convert the mass of solar units. This is easy to do, however. Just take the current number we have for m and multiply it by the number for kilograms in 1 solar unit. And then after calculating for m, which is the final step, you'll have an answer close to 4.291 times 10 to the 31 kilograms. And that's how you end up solving for the combined mass of orbiting stars.